This is section 6 of unit 2, continuous compounding. Our quote is, "The infinite. No other question has ever moved so profoundly the spirit of man." So we're going to talk about infinite in this section. The objectives are to compute interest on an account that is continuously compounded. The key terms in this section are going to be continuous compounding, which is a method of calculating interest where it is compounded an infinite number of times each year rather than every minute or even every microsecond. Another term is exponential base, or E. The exponential base, E, is an irrational number, and it is approximately equal to 2.718281828. And it's much like pi in that there's an infinite number of places you can calculate it to. And then a rational function is the quotient of two polynomials in the form of f of x is equal to g of x over h of x, where h of x does not equal 0. So let's look at an example here. Given the quadratic function f of x is equal to x squared plus 3x plus 5, as the values of x increase to infinity, in other words, they get really, really, really big, what happens to the values of f of x? In this case, we're going to use something called limit notation, okay? You may or may not be familiar with it, all right? So basically what we're saying is, what is the limit of this function, f of x, all right, as x gets really, really big or x approaches infinity? So it's the limit of x squared plus 3x plus 5 as x gets really big. Well, as x gets really big, x squared gets even bigger, 3x gets big, 5 has very little effect on this, but basically the most impact is the x squared. So as x gets really, 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 really big, if you square it, you're going to get a number that's really, really, really big, or in other words, the limit is infinity, or a really big number. So let's look at another example. Given the function f of x is equal to 6x minus 1 over 3x plus 2, as the values of x increase to infinity, what happens to the values of f of x? Well, again, we're going to use a limit function, okay? So that we're talking the limit of this function as x gets really big, all right? So we got the limit of 6x minus 1 over 3x plus 2. As x gets really, really big, subtracting 1 is going to have very little effect. Adding 2 is going to have very little effect. So we can basically ignore those two because they are going to have very little effect on this. Now we've got 6x over 3x. Well, we can cancel the x's, and what are we left with? We're left with 6 over 3. So as x gets really big, we've got 6 over 3, or simply 2. Now here's another example. Given the function f of x is equal to 2 raised to the power of x, find the limit of f of x as x approaches infinity or x gets really, really, really big. So if we do the limit again, 2 to a very large power, okay, so that's multiplying 2 times 2 times 2 times 2 a lot of times. What are you going to get? Again, you're going to get infinity, all right, or something really big. All right, now let's look at this example. If f of x is equal to 1 plus 1 over x raised to the x, find the limit of f of x as x approaches infinity. Okay, so let's look at this one. So again, we've got the limit function here, all right? Now, as I plug in let's look at this table over here. I'm plugging in different values for x. So if x equals 100, f of x equals 2.704813829. And as I keep increasing, notice what's happening to f of x, okay? And as I get way out here, which is, I believe, 100 million for x, look at the value of f of x. F of x is 2.718281786. And if I kept going, basically, what am I doing? And we are approaching this number E, okay? E is approximately 2.718281828. So as x gets really, really, really big, what are we approaching? We're approaching E, all right? All right, let's look at another example. If you deposited $1,000 at 100% interest, compounded continuously, what would your ending balance be after 1 year? All right, so here's our limit function, all right? Our principal, and obviously this is our formula for figuring out compound interest, all right? Notice what we've got here. We've got this 1 plus 1 over x raised to the x. As x gets really big, what does that approach? That approaches E, or our principal at the end of 1 year is $2,728.28. All right, if you deposit $1,000 at 2.3% interest compounded continuously, what would your ending balance be to the nearest cent after 5 years? All right, this is where we come up with our formula for continuous compounding, all right? So for continuous compounding, our balance is equal to P e to the RT. P is your principal, of course. R is your interest rate as a decimal. And T is the number of years. So let's use this formula in solving this example. Okay, so our principal is $1,000. Our interest rate is 0.023 as a decimal, and it's 5 years. So this is our equation right here. Now, again, what you're going to do to solve this is you're going to take E. It should be on your calculator, all right? And you're going to raise it to this power and then multiply it by 1,000. And that should give you, after 5 years, you're going to have $1,121.87.